All right, let's get started. Welcome, everybody. I hope that everybody who wanted to be here is actually here or just about to join us, because today we have a seminar at a slightly unusual day of the week. So it's Friday rather than Thursday. So before we start the talk, let me remind you that, as usual, once the speaker starts talking, please put yourself on mute. And when you have a question, if you have a question during your talk, then unmute yourself and ask a question. After the talk, so once the recording is off, so you don't have to disappear right away. We will still have, instead of wine and cheese, an extended period of an informal discussion and chat for those who want to participate in it. All the videos of the previous New York Group Series seminar talks are now available at the seminar website, and today's talk will be posted there as well. With that being said, I'm very pleased to welcome today's speaker. It's my old friend from graduate school days, Lisa Carbone from Rutgers University at New Brunswick, and she is going to tell us something about constructing Lie group analogs of infinite dimensional Lie algebras.
Thanks very much, Ilya, and thanks for the invitation, and thanks for changing the time to coincide with my teaching schedule. Thanks to everyone who's joined. I know people get Zoom fatigue by the end of the week. I'm going to report on work in progress on in a number of different directions on the general problem of associating Lie group analogs to infinite dimensional Lie algebras, particularly Borchard's algebras. Okay, can you see slide number 2 there?
Yes.
Okay. So if for some reason it's on scroll and the arrows are not working. So as many of you know, Kac-Moody algebras are infinite dimensional Lie algebras, which are the most natural generalization to infinite dimensions of finite dimensional simple Lie algebras. Now that topic will be in the background today. I'd like to focus primarily on a generalization proposed by Borchard's called Borchard's algebras, or also generalized Kac-Moody algebras. And these can be constructed in many important cases, from physical subspaces of vertex operator algebras, often in the context of conformal field theory. And our primary example for today is the monster Lie algebra, which admits an action of the monster finite simple group. Now, the monster Lie algebra was constructed by Borchard's and was, I think, probably one of the prototypes for the general family of generalized Kac-Moody algebras, which arose out of a new idea of Borchard's. This came up as part of his Fields Medal winning work to solve the Conway-Norton conjecture about the representation theory of the monster finite simple group. Now, Borchard's construction of the monster Lie algebra is based on the construction of Frenkel-Opalski and Merman of the moonshine module vertex operator algebra, whose automorphism group is M, the monster finite simple group. Now, in addition to its mathematical prominence and importance, the monster Lie algebra has recently, going back now sometime, but also rediscovered recently as symmetries in heterotic string theory. First by Harvey and Moore, and more recently by Paquette, Pearson, and Volpato. Now, that's an incredibly interesting new direction of study for me, which I'm just beginning to learn, and hoping to unravel some of the relationship between the mathematics and the physical structures sometime in the near future. Since Borchard's algebras describe physical symmetries, it's very important to associate to them a group, which is an analog of a Lie group. Now, in particular, this would give a global structure, which ideally we can identify as a group of transformations of our Borchard's algebra. It's very common in physical models, and if there's any physicists in the audience, they'll know what I mean. The exponential map is taken sporadically or just on individual elements, so that you never actually see the entire global group structure. So the motivation here is to construct the analog of a Lie group and all the benefits thereof. Now, I'm not aware of any constructions of Lie group analogues for infinite dimensional Borcherds algebras. I think our constructions are probably some of the first, and I'm going to describe in a number of different directions. Now, firstly, the monster finite simple group is a group with this enormous order, the largest sporadic simple group. The monster Lie algebra of Borcherds is an infinite dimensional Lie algebra, and it's a quotient of the physical space of the vertex operator algebra V, which is constructed from V natural, which is the moonshine module of Frenkel-Opalski and Merman. It's a graded module whose automorphism group is M, the monster finite simple group. And V1, 1 is the vertex operator algebra for the even unimodular two-dimensional Lorentzian lattice, 2, 1, 1. Now, the monster Lie algebra, so the previous construction is a very abstract construction, but in the important work of Borcherds and Elizabeth Jurisic, the monster Lie algebra also has a description in terms of generators and relations, with the data given by an infinite generalized Cartan matrix. G of A denotes the Lie algebra of a generalized Cartan matrix, and we take the quotient by the center of this Lie algebra. Now, this Cartan matrix is puzzling and interesting to look at. So the monster Lie algebra can be written in terms of generators and defining relations using the data in this matrix. Now, it's infinite. It's composed of finite blocks of increasing size. And the size of the blocks are given by the coefficients of Q in the modular J function, whose numbers now I think are probably quite famous. Now, let's just note that there's this little square at the top where there's a diagonal entry of 2, and the coefficient is designated with a negative number. This is a strange notation of Borcherds, which unfortunately we're stuck with. This is the only positive number on the diagonal of this matrix. And what it signifies is that there is one real root, or one root whose norm square is positive. The other entries on the diagonal are all negative numbers. They're all even numbers. And what this tells us is that there's only one real simple root and infinitely many imaginary simple roots. Now, this obviously affects the structure of the Lie algebra and all of its features, and we'll say more about this. Now, it's kind of fun to capture this information in a Dinkin diagram. This is a schematic diagram which really has the same information as in the generalized Cartan matrix. But what we have here is a complete graph on a countably infinite set, missing only one edge, namely the edge between alpha minus 1, which is the corresponds to the diagonal entry that's positive. I should have said that that diagonal entry of 2 generates a copy of GL2, as we will see. Now, this is really a schematic. There's a lot of information that's suppressed. In fact, each node here represents one block of the Cartan matrix, and the edges actually have multiplicities, which are increasing as J is increasing, J here being a natural number. So in fact, each node represents some sort of graph. Now, there are many methods for associating Lie group analogues to Kac-Moody algebras. In fact, I've spoken about this topic quite a few times in this seminar. Until recently, constructions associated to Borcherds algebras have remained elusive. Today, we'll consider the problem of associating an analog of a Lie group to the monster Lie algebra. And what we really want, if possible, is a group of automorphisms. That certainly is a relationship between a finite dimensional simple Lie group and its Lie algebra. Now, on this journey, we can't avoid discussing why the methods for associating Lie groups break down in infinite dimensions. And we'll use the example of SL2. I'll just briefly have SL2 in the background. I'll also briefly discuss the intermediate case of a Kac-Moody algebra and its associated group focusing on the example of E10, which is a hyperbolic Kac-Moody algebra with Dynkin diagram as follows with 10 nodes. It is an extension of the Dynkin diagram of E8. If you look at the vertices span alpha 1 through alpha 8, you do see the Dynkin diagram for E8, extending the long tail by one additional node. Alpha 9 would give us the affine Kac-Moody algebra E9, and extending again by one additional node gives us the Dynkin diagram for E10, which is now a hyperbolic Kac-Moody algebra. Okay, now between a Lie group and Lie algebra, the fundamental relationship is the exponential map and adjoint representation. So recalling briefly the situation in finite dimensions, let G be a simple Lie algebra, let capital G be the corresponding simple Lie group. Then there's an exponential map, which takes an element X to the well-known series, X to the K over K factorial. Now, when G is finite dimensional, this is a finite terminating series when applied to the endomorphism add of X sending Y to the bracket of X and Y. So then the map from the Lie algebra to the GL of G, taking X to add X. So this is called the adjoint representation. And when we apply X to add X, in the finite dimensional case, we're going to get a finite sum. So this series, Y plus bracket of XY plus 1 over 2 factorial, add squared, operating on Y, and so on. This is a finite sum in finite dimensions, and thus X add of X is a well-defined automorphism, a well-defined element of add G. And so this is how we construct the so-called Chevalley groups of adjoint type. Now let G be a simple Lie algebra, and suppose we have a Chevalley basis for G. Now this is a basis for the Lie algebra in the usual sense. It has a special property that with respect to this basis, the structure constants of the Lie algebra are integers. Let add once again be the adjoint representation, taking X to add X, which operates on elements of the Lie algebra as the bracket. If we take scalars S and T and C, then X, S, add looks like the identity matrix. So these, we now have matrix representations, and you've probably seen the matrix, the three-dimensional matrices for the adjoint representation of SL of the Lie algebra SL2. Identity plus S add E alpha plus S squared over 2 add squared E alpha and so on. And the same for F alpha. Now these are finite sums for a simple Lie algebra, well-defined elements of Ort G. And so we may consider the group generated by X S add E alpha and X T add F alpha, where alpha ranges over the set of roots, which is finite in this case, and S and T are our complex parameters. So considering this group, we get a representation, which we call add with a capital A, of G in the automorphism group of the Lie algebra, generated by X add. Now the Chevalley group of adjoint type is defined to be the image of this group in Ort of G. And so for the Lie algebra SL2, the Chevalley group of adjoint type is SL2 C modulo plus and minus the identity, otherwise known as the projective special linear group. Okay, now suppose we want to carry out the same idea for infinite dimensional Lie algebras. And let's talk about the Kac-Moody case for the time being. Now, it turns out that the adjoint representation of a Kac-Moody algebra has this nice property. It's locally nilpotent on the simple root vectors, and there are only finitely many of these. So, so if we have a basis of simple roots, excuse me, if we have the generating set of simple roots, not a basis, then add EI and add FI to some suitably large powers are vanishing. Now this mimics what happens in the finite dimensional case. And thus exp add EI and exp add FI are also finite sums in the Kac-Moody case. So this is a quite a nice setting for generalizing what we just described in the finite dimensional case. We can then consider the group generated by exp s add ei and exp t add fi for the simple root vectors ei and fi, ranging from 1 up to L, and there are only finitely many of those. And as before, we can define the adjoint group to be the image of the group generated by these elements in the automorphism group of the Lie algebra. So there is such a notion as the Kac-Moody group for E10, the Kac-Moody group of adjoint type over the complex numbers. It's a subgroup of automorphisms of the Lie algebra E10. And so when people say Kac-Moody groups, this is possibly one of the more common ways to construct a Kac-Moody group, although there are very many different approaches, as I'll discuss a bit later on. Now, what happens to exp-add for Borchard's algebras? Well, that whole wonderful program for constructing transformation groups no longer works. A root is called real if its norm squared is greater than or equal to 0, and imaginary if the norm squared is less than 0. So in the Cartan matrix for the monster Lie algebra, we saw one diagonal entry, which was positive, and we can view the diagonal entries as the squared norm of simple roots. So there's only one real simple root for the monster Lie algebra, and the remaining set of simple roots are imaginary, and there are infinitely many of them. Now, the simple roots of a Kac-Moody algebra are real, while Borchard's algebras in general may have imaginary simple roots, and the monster Lie algebra has infinitely many of them. Now, unfortunately, the adjoint representation is not locally nilpotent on imaginary simple root vectors. The same, of course, is true in Kac-Moody algebras. If we drop the word simple, add is not locally nilpotent on imaginary root vectors. Kac-Moody algebras do have them. They're just not taken in the generating set. Now, in Borchard's algebras, we do include these imaginary roots in the generating set, and so exp-add turns out to be an infinite sum. It's not a well-defined automorphism of the monster Lie algebra or any Borchard's algebra, so we need a different approach. Now, another way to construct a transformation group in finite dimensions, which also works in the Kac-Moody case, is to replace the adjoint representation by a highest weight representation. So the adjoint representation is the Lie algebra acting on itself by the bracket. So we can consider instead an external representation, some representation space V with a representation of the Lie algebra on that vector space. And if we carry out the same program, the group we construct in this case is called a simply connected Chevrolet group. Now, the simply connected Chevrolet group corresponding to SL2 is isomorphic to SL2C. And it turns out that a similar program is possible for Kac-Moody algebras. They have integrable highest weight representations, rho, from the Kac-Moody algebra G onto on a vector space V and defining homomorphism G from G onto NV. And these integrable highest weight representations are locally nilpotent on simple root vectors. They won't be on imaginary root vectors, but on the simple root vectors, the image rho of EI and FI to some suitably large power is vanishing. So we can take exponentials, x rho EI and x rho FI are finite sums and hence well-defined elements of NV. So we can construct a simply connected group for Kac-Moody algebras, in particular E10. An analog of a simply connected Kac-Moody group, E10, with the index V, can be constructed over fields and over Z. Now, this method does require a significant amount of additional external data. we use an integral form of the universal enveloping algebra, an integrable highest weight representation of E10, and an integral form of the representation space V. Now, simply connected groups have been constructed in joint work with Howard Garland over arbitrary fields, and in joint work with Dongwen Liu and Scott Murray over the integers, following an idea of Tietz. So Tietz proposed a program of this type, but he didn't carry it out himself. Now, I'll just mention that there are many other constructions of Kac-Moody groups over fields. Some of them may be able to be defined over Z. And this is now a vast subject spanning many authors and techniques. And many.
So which object here was infinite dimensional from which you started, or I mean, have you Googled already? So I've sort of missed.
So here we have the hyperbolic Kac-Moody algebra E10.
And
this is an infinite dimensional Lie algebra.
So that's the infinite dimensional object, and that's the sense to which you are associating this group by this new method. And I see. Okay, thanks.
Yes. I didn't mention in the beginning, but you know, just as the monster Lie algebra has shown up in physical models, so has the Lie algebra E10, and there are some important conjectures about the role of E10 in the unification of string theories, and particularly over the integers. So studying the group theory of E10 over fields and of characteristic 0 and over Z is an important question. So as I mentioned, this is now a vast subject, building on the seminal works of Tietz and Garland. I've been interested in this subject for quite a long time, and there's still many things to learn and many things that we don't understand. Now, there's another way to construct a group, and that's just simply to write a presentation given by generators and defining relations. Now, in the finite dimensional case, Steinberg gave a defining presentation for finite dimensional Chevrolet groups of both adjoint and simply connected type. In fact, you do it essentially the same way, using the adjoint representation instead of a highest weight representation. This can be done over any commutative ring. And now, Tietz also generalized this idea to infinite dimensions, giving generators and relations for Kac-Moody groups over commutative rings, generalizing the Steinberg presentation. Now, the funny thing is, this is an incredibly abstract result. He abstractly tells you what the defining relations are, but he doesn't tell you how to actually find them in practice. And it turns out that for some important examples, there's no guarantee that the defining relations can be determined explicitly in practice. And in the example that we're most interested in E10, in fact, there's an interesting paper of Daniel Alcock, which shows the impediment to actually being able to write down the defining relations for E10 because of the problem of enumerating the so-called pre-nilpotent pairs. Now, Tietz's presentation also contains a lot of redundancy and can be reduced significantly. And in joint work with Daniel Alcock, we obtained a simplification of Tietz's presentation for the group E10. And we got very, very lucky in this restricted family of cases, which includes E10. We obtained a finite presentation for E10 over Z. So this infinite dimensional hyperbolic Kac-Moody algebra, we gave finitely many generators and finitely many defining relations over Z. And the generators are indexed only over the Dynkin diagram. That can't be done for all Kac-Moody algebras, but we obtained a simplification of Tietz's presentation for a wide class of hyperbolic Kac-Moody algebras. Now, so I guess this is the first thing that we tried to do for the monster Lie algebra, and we'll see that there is a way to get an analog of the Steinberg presentation and Tietz's presentation for the monster Lie algebra. It raises more questions than it answers, but this is one approach to associating a group. Now, let's just summarize the situation if we apply these methods to the monster Lie algebra. What are the main obstacles? So we've discussed three different approaches to constructing an adjoint group just by taking the group generated by exp_add of the simple root vectors. Well, it doesn't work for the monster Lie algebra because the adjoint representation is not locally nilpotent on the imaginary simple roots. This sum is infinite and not a well-defined automorphism of the Lie algebra. Now, to construct a simply connected group, so to replace the adjoint representation by a highest weight representation, there are no highest weight representations that are locally nilpotent on the whole of the monster Lie algebra. So if we try to look at taking exponentials of the images under a highest weight representation, we don't get a well-defined automorphism of the monster Lie algebra in general. Okay, well, what about trying to write some generators and defining relations for the monster Lie algebra? Well, we can actually try to mimic the Steinberg presentation, but so what's it going to give us? It'll give us an abstract group. In general, you can't expect such an abstract group to be a group of automorphisms. And because we really want the analog of a Lie group and we're interested in physical applications, we really want to stick as close to possible as an automorphism group. Now, over time, this has been a very long-term project with a lot of starting and stopping and a lot of failures and resurrecting things, but we now have new approaches to address each of these obstacles. Now, just to describe our approaches in those different directions, let's just talk a bit about the structure of the monster Lie algebra without getting into too much terrifying detail. Now, the monster Lie algebra has a usual root space decomposition, but it has another direct sum decomposition, which was proven by Elizabeth Jurisic. It can be written as a direct sum of a GL2 corresponding to the one positive entry on the diagonal of the Cartan matrix and two free Lie algebras, U imaginary plus and U imaginary minus, which are free Lie algebras on countably many simple imaginary root vectors of M, indexed by sets S and S prime. And I wrote down what these generating sets look like. They're a little bit terrifying. EJK is one of the simple root vectors, as is FJK. And then we take powers of add E minus 1, which is the simple root vector for SL2. So E minus 1 and F minus 1 are the basis for, they're in the basis for the GL2. We take powers of these operating on the imaginary simple root vectors EJK. So we get these longer and longer brackets, add of E minus 1 to a power. Eventually this will vanish because the adjoint action of GL2 on the monster Lie algebra is locally nilpotent. So J minus 1 is the last exponent that we get in this family, but this is indexed over the set of natural numbers J. K is also constrained by the coefficients of the modular J function. So we have this multi-parameter family and we have these arbitrarily long sets getting longer and longer, one for each natural number. Nevertheless, this decomposition plays an important role in the task of associating a Lie group analog. And in fact, in every approach that we've tried, this decomposition plays a critical role. Now, a picture that I've stared at for a very long time, thanks to Scott Murray, who came up with this diagram, which is a slightly different diagram than you might see in most of the literature on the monster Lie algebra. The root lattice should be an infinite dimensional lattice because there are infinitely many roots in the Lie algebra. But we may identify the root lattice with the Lorentzian lattice of type 2, 1, 1, which is z plus z with this unusual bilinear form. And with this identification, we get the following root diagram. The real roots are denoted by the blue nodes, and there are only two of them, alpha minus 1 and minus alpha minus 1 in the second and fourth quadrants on the blue hyperbolas. All the other roots are imaginary. The imaginary simple roots are indicated with a bold red node. And so this is the line through x equals 1 on the x-axis. And the other roots with an index of the form L, JK, these are imaginary roots. They're not imaginary simple roots, but we use them in the generating set for Jurisich's decomposition. So staring at this picture does actually reveal some incredibly important things about the monster Lie algebra. Let's just mention a nice fact that, so these red hyperbolas are, they're like the spheres of constant radius, except that they're hyperbolas. And so you can imagine, so there is a Weyl group action, but the Weyl group, so if we're in a Kac-Moody algebra, we would see the Weyl group acting by translations along these hyperbolas. But the Weyl group here is extremely small, and it turns out to be only the Weyl group of GL2, which is a very puzzling thing in itself. But anyway, that's not really crucial for the discussion today. Now, motivation for the following direction of attack comes from Kac-Moody algebras. So the monster Lie algebra also has the usual triangular decomposition as a direct sum decomposition of a Cartan subalgebra H and positive and negative spaces n plus and n minus. And the n plus and n minus are the direct sums over the positive and negative roots of all the root spaces. Now here, I guess it goes without saying that the set delta is infinite. The root spaces m sub alpha, however, are finite dimensional. And this is similar to the setting in the Kac-Moody case. And one thing we learned from Kumar is that one can take a completion of an infinite dimensional Lie algebra in the forward direction or the positive direction, the completion denoted with a hat, m hash, by replacing n plus by the formal infinite product of all the positive root spaces, which we can also index over the set of natural numbers by suitable grading. And so we can describe it either as indexed over the set of positive roots or over the set of natural numbers. Each homogeneous component is finite dimensional, and we've completed in the positive direction to obtain n hat plus. This turns out to be naturally a pro-nilpotent Lie algebra. What we mean by that is an inverse limit of finite dimensional nilpotent Lie algebras. And it turns out that this is actually quite a manageable situation, and we can work with this in an analogous way to the Kac-Moody case. Certain things are feasible even in the case of Borch's algebras. Now, of course, introducing these infinite products, well, when you want to multiply things together, you start having very big problems. And so it leads us to the following notion. An infinite sum of operators is called summable if it reduces to a finite sum when you apply it to any y on which it's operating. So an infinite sum of operators is called summable if it reduces to a finite sum whenever you apply it to a y value on the space on which the operators are acting. Now, let's take an imaginary simple root vector of the monster Lie algebra. As we've seen, exp_add of EI is an infinite sum. Now, we don't have this problem in the Kac-Moody case because exp_add of a simple root vector is finite. But if we did have an imaginary root vector in the Kac-Moody case, we also get an infinite sum. So there is some overlap in the considerations here. Now, in both the Kac-Moody case and the case for Borch's algebras, including the monster Lie algebra, we may say that exp_add of EI is prosummable, since if we apply exp_add of EI to any y in n hat, then exp_add of EI operating on y reduces to a finite sum when restricted to any component, any finite dimensional component of the completion. Okay, now this is very exciting. Well, we don't have automorphisms of the monster Lie algebra, but we will be able to construct prosummable automorphisms of the completion. And this, I think, is the best that one can hope for. And this turns out to be quite a manageable construction. Okay, now our first good news after talking about the difficulties for more than half an hour. So the first good news is, in joint work with Elizabeth Jurisic and Scott Murray, we have constructed a complete pro-unipotent group of automorphisms of the completion. So we denote this by U hat. Now the generators of U hat as a topological group are power series with constant term 1. And the elements are prosummable automorphisms of M hat. And they look like, well, they're an infinite product. They're an infinite product of the form exp_add of xk for xk in nk hat, which is, it's an infinite product over I greater than or equal to k of the root spaces M sub I. Okay, now what's going on here? Well, an element of the completion of the monster Lie algebra is an infinite formal sum. But when we apply group elements of this type, if we apply G to X, we get something finite when restricted to any component, M sub K, actually that should probably have a hat on it, any finite dimensional component of M hat. Now, what are these elements? We say they're automorphisms of the completion. Well, they're elements of infinite order that act on the completion by shifting the root spaces with respect to a suitable grading. And this turns out to be something like this has come up with Kac-Moody groups. Now, for Kac-Moody algebras, complete pro-unipotent groups have been constructed by Kumar and Russo. Something like this was in a very early work of Tietz, probably Tietz's first paper on Kac-Moody algebras, where he constructed a Kac-Moody group as a subgroup of the multiplicative group of the completion of the universal enveloping algebra. Now, this then disappeared from the literature and from Tietz's subsequent papers. But I think this actually was probably the right idea. His group constructions thereafter turned out to be very restrictive. And I mean, they're suitable groups for a lot of considerations, but for generalization, the group that Tietz constructed is not, well, it has the problems that we've spoken about today. He did have the correct idea early on, in my opinion. Now, given that we have this adjoint group in joint work with Alejandro Giannori, Elizabeth Jurisic, and Scott Murray, it turns out that we can't entirely replace the adjoint representation by a highest weight representation, because there are no highest weight representations for which the action of the simple root vectors is locally nilpotent on the whole monster Lie algebra. Now, thanks to Jim Lepowski and Elizabeth Jurisic, I learned about such representations on a subalgebra of M. So if we consider the decomposition of Jurisic of the monster Lie algebra into GL2 and two free Lie algebras, U imaginary plus and minus, if we take the GL2 plus U imaginary plus, it turns out that there are the so-called standard irreducible modules constructed by Jurisic, Lepowski, and Wilson. These are locally nilpotent, the standard irreducible modules are locally nilpotent on this subalgebra. And therefore, we get to construct the analog of a simply connected Chevrolet group on this subalgebra of the monster Lie algebra. Now, the choice of highest weight module here is a highest weight module of GL2 and a choice of highest weight lambda. Okay, that's the good news. The bad news is this is the craziest group I've ever seen in my lifetime, where the group construction is defined the group multiplication is defined recursively. And just to multiply two group elements together, you probably need a computer algebra system such as Magma or something of that type. So even though this is an analog of a simply connected group, and I'm happy to report that such a construction is possible, I don't know a lot about this group, but the group construction exists, and we hope to be able to tell you more about it in the near future. Now, generators and defining relations. I have actually spoken about this presentation of a group for the monster Lie algebra in Manhattan Algebra Day, going back a couple of years. In joint work with Elizabeth Jurisic and Scott Murray, we have constructed a Lie group analog by generators and relations. And this is really the analog of Tisa's presentation for Kac-Moody groups. On the other hand, our group does contain generators associated with the imaginary roots of the monster Lie algebra, and we have given relations between them. Now, such generators do not appear in Tietze's presentation for Kac-Moody groups or anywhere else in Kac-Moody theory, although Rousseau's complete pro-unipotent groups for Kac-Moody algebras do have a notion of imaginary root groups, just not given in terms of generators and relations. Now, this group does have subgroups associated to the positive and negative imaginary root vectors. These are free products of additive abelian groups, isomorphic to the additive group of the field, one for each imaginary root. Now, if we consider these over Z, these groups become free. So there are infinitely generated free subgroups, U imaginary plus and minus, when considered over Z. And this mimics the decomposition of Jurisic, including the free Lie algebras, U imaginary plus and minus. Okay, now this is an abstract group. We were very happy when we could define a group. We were extremely disappointed when we realized that it could not be a group of automorphisms of the monster Lie algebra. Now, probably the hardest theorem in this whole subject is to show, however, that the unipotent part of this group, G of M, generated by the positive imaginary root vectors, actually embeds in this pro-unipotent group we constructed, U hat, and hence embeds in the automorphism group of the completion. So we have a group by generators and relations. It can't be a group of automorphisms of the monster Lie algebra. However, it does embed in the automorphism group of the completion. And so the unipotent part is acting by shifting transformations in some sense. So there's still certain things to understand. Now, not surprisingly, something very interesting happens when we consider this group over Z. There is a natural discrete subgroup, which is an analog of the modular group. It's also an analog of E10 over Z, which is kind of a modular group in certain supergravity theories. And there are conjectures about the role of that in supergravity and the unification of string theories. Now, what is this group? Well, it's obtained by restricting the generating set and the group relations to those that can be written down over Z. And as we've already mentioned, the unipotent subgroup of our generators and relations group has a natural image in the automorphism group of the completion and is a countably infinitely generated free group. Now, certain people pressed me to investigate this group, including Igor Frankl, who pointed out that this discrete group may play a role in describing the quantum symmetries of heterotic string theory in the models of Harvey and Moore and Paquette, Persson, and Volpato. Now, there's also work by Ed Witten and subsequently by Andrew Duncan and Igor Frankl on chiral quantum gravity in 1+2 dimensions, where the monster plays a prominent role. So there are a lot of natural open questions coming up in the future, and a lot of things that we still wish to study. Now, as a transformation group, the group that we constructed by generators and relations, as we mentioned, it doesn't act as an automorphism group of the monster Lie algebra. It embeds in our pro-unipotent complete group, which also embeds in the automorphism group of the monster Lie, of the completion of the monster Lie algebra. So the unipotent part of our group, given by generators and relations, is an automorphism group of the completion. However, there's this nice sort of, there's this nice corollary for the GL2 subalgebra. Its action, its adjoint action on the monster Lie algebra is locally nilpotent. And thus, the GL2 subgroup, the GL2C subgroup of our group G of M, acts on the monster Lie algebra as inner automorphisms. Now, it's kind of an easy corollary, but that was not previously known. Another corollary is that with respect to the generating sets that we've chosen for the free Lie algebras, U plus and minus, the group GL2C, it's not exactly the matrix group GL2C, it's a representation. It has different generators, but we can kind of model it by 2x2 matrices. So a certain isomorphic copy of GL2C acts on the free Lie algebras as inner automorphisms. Now, certain of you in the audience may know better than me. I don't think we have seen a result like this in algebra, where you've got a matrix group acting on free Lie algebras as inner automorphisms. Please correct me if I'm wrong, but that seemed to be a nice, easy corollary, but it's with respect to a particular generating set. Now, just to finish up, there's another fourth approach, and this is joint work with one of our students at Rutgers, Hong Chen, Elizabeth Jurisic, and Scott Murray. Suppose that we just try to construct automorphisms of the monster Lie algebra by hand. Suppose that we don't use these fancy group constructions, but suppose that we just try to construct automorphisms explicitly. Well, playing around and literally getting our hands very dirty with constructions, looking at involutions on the monster Lie algebra, well, we encountered a representation of the monster finite simple group. And I don't think that this representation of the monster finite simple group in the automorphism group of N is previously known. Now, we did this via permutation representations of the monster finite simple group. The smallest permutation representation is permutations on this large number D, D points. Now, Now it's just kind of playing around with coefficients. This number D is, I think it's on the next slide. This number D is lies between C14 and C15, these coefficients. And these coefficients for the modular J function obviously appear in the generalized Cartan matrix, but also as the dimensions of imaginary root spaces of the monster Lie algebra. So we obtain an embedding of the monster finite simple group M in the automorphism group of the monster Lie algebra via the smallest permutation representation of the monster finite simple group. So M embeds in the symmetric group on D letters, which we can embed in the symmetric group on C15 points, which using other ideas of Scott Carnahan embeds in the automorphism group of the monster Lie algebra. And this gives us a representation of the monster finite simple group in terms of permutations, sigma, k comma k prime, lying between 1 and this coefficient C15, where these permutations permute the indices on the imaginary simple root vectors. Now, I've said this before, but we were very pleased when we realized that we could construct such an embedding, such a representation of the monster finite simple group in the automorphism group of the monster Lie algebra. This was not previously known, but on the other hand, this result is not as good as it sounds. It is constructive, but not illuminating. We simply got a representation that permutes the indices of imaginary simple root vectors. Well, we'd certainly like to see something of the monster finite simple group in this representation. So we need to go somewhat further. And that's the end of my presentation. I've just got a comment about future directions, where I'm starting to see how this might go further if we're able to construct an integral form, MZ, of the monster Lie algebra M. Associate a group to the integral form of the Lie algebra, determine its relationship with the natural discrete subgroup that we already have, GZ of M, and its relationship with the monster finite simple group M. We could then refine our representation of capital M, the monster finite simple group, in the automorphism group of the monster Lie algebra. We could refine it to an embedding of the monster finite simple group into the automorphism group of the integral form. This should give us a much sharper embedding and hopefully tell us something about the monster finite simple group. Now, there are other obvious directions to construct our group in the setting of Hopf algebras, because there really is a Hopf algebra construction sitting in the background of what we've done using a completion of the universal enveloping algebra. We just sort of have to turn the handle and say what that construction really looks like. And having come this far for the monster Lie algebra, we can certainly apply our methods to associate groups to other Borcher's algebras. Certainly the things follow almost immediately for the baby monster Lie algebra and other Borcher's algebras of interest. So I thank you so much for your attention so late on a Friday, and there's a photo of what's in my backyard right now.
Great. Thank you very much, Lisa. Let us thank the speaker for a very interesting talk. Thank you. Okay, so now the floor is open for questions. So anybody who is who wants to ask a question, you're welcome to unmute yourself and ask your questions now.
I have a quick question. Can you hear me?
Yes.
Hi, Lisa. Thanks for the great talk. I have a question relating to your construction of the simply connected version of the groups.
Yep.
You said that there you were naturally able to make use of some highest weight EREPs studied by Jurisic and Lepowski. And I was just wondering, so I don't believe that So the while vector is a highest weight representation, or is the highest weight vector for a representation of this type?
Right, correct.
I was just wondering if you could sort of imagine some sort of construction where that that representation or that highest weight vector played a role.
Would absolutely love that. This is a representation on the tensor space, and once we gain some familiarity with this this tensor representation, where the group multiplication is defined recursively using tensors, it's really quite something. I think once we gain some familiarity with it, we'll see how to make other constructions and play around somewhat so that we can do more meaningful things such as what you suggested, which is a great idea.
Thanks a lot.
All right, other questions?
Lisa, this is what is your paper in the archive? Like,
Yeah, there's one paper in the archive, which is, it's kind of a research announcement. It gives somewhat of an overview similar to what we discussed today. Yeah, the main paper describing all these different constructions is technically challenging. And we're working through some of the difficulties.
All right. Okay. So if there are no other questions, let us thank Lisa again. Thank you.
Thanks so much for the opportunity, and it's great to see everyone online.
So now I'm going to stop the recording.